now we will talk a bit about Jupyter notebooks or Jupyter Labs and how we can process the data using Jupyter Labs while constructing a documentation about our workflow, a more rich documentation about our workflow. And this is really useful for data reproducibility in the future. For example, adding this as an ancillary file for a journal, which contains the data references and also how you prepare the data, how you process the data. And so now we will just use an example of high-res processing, a very basic example of high-res processing from raw data, the level 0, to a map projected version, the level 2 product. But first, we need to understand a bit better how high-res takes the images, acquire the images. This is because it's necessary to understand first, even in a general way, how the instrument acquired the data, because then each instrument has a different processing step, and each different processing step can be customized to further improve eventually the data. For example, here, ARISE, one thing, first of all, we have two main softwares that are used for processing the data. The first one is the integrated software for imagery and spectrometers that is called ISIS, developed by USGS and is completely open source, while the other is the NASA AMES stereo pipeline that is specifically—
Sorry, Giacomo.
Yep.
Sorry if I interrupt you. Is it possible to raise a bit the volume of your mic?
Okay. I will try to raise my voice also a bit. I've always problem with my voice. Sorry. I will try to speak louder. That's it. Can you hear me better now?
Yes, very well.
Okay.
Thank you.
Okay. Yeah, I'm sorry. Those two softwares, the NASA AMES stereo pipeline, ASP, is mainly used for processing visible images to create DTM using stereogrammetry and shapes from shading techniques. At first, we will use only the ISIS software to create the map projected version of the data, and while ASP has a completely different workflow and in some ways can be even cumbersome in respect of ISIS because there are way more parameters, but we can talk a bit this later if we have time. Otherwise, we can follow up on Discord. So ISIS and ARISE, instrument is composed by several charged couple detectors that are simply the camera sensors, which are differentiated in three main groups. The first one is composed by two CCD filtered. Each CCD is has a filter in front of it, and is differentiated by the wavelength which the filter is sensible. For example, two filters are sensible to the near infrared wavelengths, 10 are sensible to the red wavelengths, and the last one, are sensible to the blue and green wavelengths. And all of these can be used all together or separately to reconstruct, for example, an RGB composite. But of course, as mentioned yesterday by Ricardo, since Mars is mostly red, we have more red filters to acquire a larger image with larger details. In fact, IRIS can reach up to 0.3 meters per pixel of spatial resolution in its best configuration. So it's really, really high resolution. But also, all the data are really heavy, not only to visualize, but also to process. So it's also a bit complicated to reconstruct the image, but luckily, all of this is automated by the ISIS commands. So just to see another view of the CCDs, if you can see also that each CCD has a slightly overlap with the others. And this is necessary to know exactly the position of each CCD in respect of the other, and then reconstruct the final image, as we can see in this schematic of the red acquisition channel. You can see the red channels that are acquiring on the surface long stripes that are overlapping one of each other. And then at the end of the workflow, we will have the full image, not only the stripes. There are several commands that needs to be executed. Some are specific to arrays, for example, the high to ISIS or the high cal or the high stitch, while others like the spice init are generally and in common with other processing instruments like CTX, CRISM, and so on. And all of those are integrated with ISIS. Then at the end of this processing, we will have a file that is in the format of ISIS, file format of ISIS that is called cube or CUB. And then this cube, even if it is compatible with GIS software like QGIS and ArcGIS, we can convert it into more usable or standardized format like GeoTIFF, JPEG 2000, and so on. And while also manipulating it further, like changing the spatial resolution, reprojecting, and so on. And at the end, imagine from these stripes, we will end up with a map projected image. This is a cropped version of the full image. So here are really basic references about the ISIS software and the Cala series, that is a wrapper developed around ISIS. So the advantage, as mentioned by Carlos, the advantage of Jupyter Lab and Jupyter Notebooks is that you can implement both a description of the code and the code itself, but not only a description, even a discursive description. For example, here I implemented this overview of the arrays processing. While here I can implement some comments about my code. For example, here I'm importing the basic packages and utilities and functions. Then I define some functions and then describe what those functions do. And then I can move on to the proper processing. But first, I can also describe what the user needs to input or needs to provide as an input. For example, I will zoom in a bit. We will ask the user to provide the folder. So here in Jupyter Lab, I shared different folders. For example, my data is in this folder. So user must to provide, oops, where it is here, must provide the folder where the data is stored. Then where the final results needs to be written or outputted. And here I just define the source. So I want in the same folder. Then I can provide the map template. Map template is a file necessary to map project the data, which contains all the information regarding the reference system that we want the map projected version of the image. And then we can provide as many variables as we want or as we need. Then we move to the proper processing. Here we can just list all the files or the CCDs, because each CCD is numbered from 0 to 10, in this case to 9, in this case, because are 10, and the numbering in Python starts from 0. In general, numbering starts from 0. And then we have 2 channels, 0 and 1, for each CCD. So we can check it up that we have all the data, and then we can move to the initial phases of the process. For example, here we are converting all those images in parallel from the EMG, that is a binary format provided by the planetary data system, or provided in the planetary data system, which contains the raw data for each CCD, and we convert into cube file. And then we can run this in parallel. We define the function, we define the function to run it in parallel, and we execute it. Then we move to one of the initial most important step, that is the data calibration, that is intended to be performed on each channel to correct a lot of distortion and signals that can be occurring during the acquisition phase. So this is really important phase. Then we can easily run it in parallel for each CCD, since those are independent one to each other. Then we can stitch all the CCDs together, or at least the channels, because we can remember that each CCD, we have 10 CCDs, each CCD is composed by 2 channels each, and then here in this phase, in the stitch step, we merge all of those channels for each, all of those channels for each CCD. So we will merge the CCD 0 plus 1, CCD 1 plus P3, and so on. Sorry, CCD 2, 0, and 1, and so on, for all the CCD pairs, channel pairs. And then we can also not only describe what the functions are doing, but also we can add comments to the specific line. For example, here, name of provide additional information about the parameters that we are using. Because, for example, the function can accept several parameters, and we want to address the audience that is reading the notebooks, which are the parameters that we use to process the data, so they can replicate our exact results. And this is really useful because you can do it also using a separate README file with a batch script or other scripts that do it automatically or within your code. But implementing documentation within the code itself, it's pretty confusing sometimes, especially if you have a lot of parameters that you want to address and describe. And also, if you want to implement images, images cannot be implemented into a plain README file, for example, or at least you can do it, but then again, you need a specific reader, or it's still pretty much confusing in some cases. Here, instead, we can combine both of two words, having the code nearby all we want for the documentation. So parameters, images, other codes that we can comment, and so on. So moving on from the parallel stitch, we can do this in parallel. Here we do it, and then we do this additional step that is spicy kernel initialization. The spice kernels are, let's say, like a database which contains for every orbiter, every instruments that have been used in the past, and probably in the future, all the future instruments that will be launched and used will have a kernel inside this spice kernel database, which contains all the informations relative to the spacecraft and camera models. So, for example, where was the spacecraft when the image was acquired, how it was oriented, where was the sun, and all other parameters that help the other further commands of ISIS to reconstruct exactly the place where the orbiter was when it acquired the images. And then from that, you can reconstruct with a certain degrees of precision, as Trent also mentioned yesterday, where you are looking at. So for example, if you don't do this, you cannot do the map projection because you cannot link together the image with the proper location on the surface. So this is a very important step. And if you want any kind of map projected version of the file, you need to use spicy initialization. It's interesting, spicy init, because they have two ways of operating. One is using web interfaces, or at least web databases, and so you don't need the ISIS data. For example, if you're running on your own computer, you can use spicy init web database, or you can use the ISIS data on your computer or a network stored drive, or so on. So it has also some additional customization that at the moment we are not involving yet, we're not explaining yet. But for example, here I'm using a flag, an attribute to an argument to define if my spicy init needs to use the web interface, web database, or the local one. And we can customize it as we want. For example, in this case, I want to use the web database. And so I can also describe which is spice kernels. For example, let's imagine that this is more global for a specific workflow. We can implement all of those descriptions. But then we can move to another very important step, that is the no projection, that is the correction of the cube using the data retrieved by the space kernels and correcting the cube for the camera distortion. So in the step before, we corrected by the camera noise signal. Then we correct them for the optical deformation produced by the lens and also by the sensor and the target spacecraft position and geometrical properties. So we can do this in parallel too. We can, it's pretty straightforward. We can choose which image, which CCD we want to correct all of those images to be the centered ones. We choose exactly the same, the one in the middle, and then we can do that. As you can see, this step is performing quite a bit of time if you compare it with the others. For example, this one took 4 minutes, the previous one only 20 seconds, and the other one, no, this 1 millisecond, for example, and so on. So there are several time requirements in respect on the machine you are working on. For example, here I'm working on a 40 threads machine or 14 cores. So it's kind of fast, but if you're running your laptop that may have less CPU cores, it may be slower. And also it depends on the data size, because HiRISE is pretty heavy. CTX is kind of lighter, but is larger, so it's comparable. But those are all the more technical aspect that we can talk about eventually in Discord channel later on. So if you have any question regarding the proper processing, keep it for the Q&A or the follow-up on Discord. So after this camera distortion correction, we move to the proper co-registration of all of those stripes that are related to each CCD, because we need to co-register and be sure that the overlap of these images co-registered, so it's correct, and there are no misalignment. And also in this phase, we can derive the signal noise or the jitter caused by the sensor itself, because each CCD have its own randomly generated or like say, you can say that are peculiar to each CCD signal noise. And here we can characterize by comparing to the other CCDs, and then we can remove that to have a better image. And so we can do this also in parallel. It's pretty fast. And then at the end, or almost at the end, we can reconstruct this whole image, merging on all of those overlapping CCDs or these overlapping stripes. So we can do that easily. This is an implementation of the main Python function that have been developed by the USGS and is embedded into the ISIS command line functions. And then we can also define how this combination or this mosaic works. And then at the end, we will have this mosaic that is composed by several stripes that have different values. So we need to normalize also this cube to have an homogeneous, or at least hopefully homogeneous whole image that contains all the processing steps that we performed before. So the data calibration, the, camera distortion correction, spacecraft correction, and so on. So we can do also this, and then we will end up with this huge cube that can be even heavier than the original data source. For example, in this case, we have a cube file that is 3.6 gigabyte, and I can show you in QGIS. So this is the whole cube that we've processed and map projected. But since this map projection, or eventually you are interested in using only a small portion of this region, you're not interested in the whole Jezero crater fun where the 2020 Perseverance landing site. This is the path from the USGS, from NASA, sorry. But you are interested in only a specific portion, you can do that before the map projection itself. And this will save you a lot of time. And this is really interesting because, for example, I just described it here that we can do this map projection, this crop, by selecting the lines, and so the height and width values where we want to crop it. And then we can crop it before the map projection itself, because the map projection considers the highest and time-consuming, not parallelizable functions of ISIS. And so in the whole processing, the map projection is the most time-consuming. The other processing, even at the highest resolution, is very fast. It's a matter of minutes. While the come-to-map, the map projection, that use the come-to-map command, may and to take up even one day to do that, or several hours, depending on the size of the image, the resolution, and other parameters. So reducing this time can be very helpful, especially if we are interested only in a small portion. So we can do that, and then we can, it's very fast, this cropping, and then we can proceed to the proper map projection. This map projection use so-called map template, which simply contains the coordinate reference system that we want to use. And we need to know which are the coordinate reference system that we want to use, because at the end of this process, we will not end up with an image that is perfectly placed where the real data is, or where is in the real world, because there are always some issues related to the camera acquisition. Some others are introduced by the reference system, as you saw probably in the presentation by Angelo yesterday, in which you can have different deformation in different places depending on the reference system that you're using. So it's really necessary to know where you are, or what you are using to process those images, and to map project those images. But you can always have control where your projecting is, and which file you are using, which parameters, and so on. Then you can just run it, and it will, for example, this is a really small crop. It's really fast, 37 seconds. And then you will have this cube file. So we are still working on the ISIS cube file format, which is still compatible with GIS software. But for us to be further use, maybe we want to convert it into another standardized format like GeoTIFF, JPEG 2000. And we can do this still in our notebook. For example, here, just close this one. We are using GDAL to convert from a cube file into the GeoTIFF. And then we can also go further. Instead of moving to GIS, for example, here, this is the final crop that I've created before with this notebook. So I can see that it's not perfectly map projected, because the rover path that is correctly placed is slightly moved, is not really centered. So we need to still further processing this. But here in this case, we were just looking at the results of the image itself. So if it contains holes, if it has some huge deformation, or so on. So the quality of the data itself. But we can do this also on using Python. We can read this using RioXarray. That is another library similar to GDAL. We can use GDAL, raster.io. We have several libraries that we can use, and it's upon the user to use the one you it's more familiar with. For example, here using RioXarray, you can see some metadata like the wavelength, the channel, the coordinates. This is a projected reference system. So we have the projected coordinates in meters and the band of the image. In this case, we are only working on the red channel. So only one band, that is the red band. And then you can plot this. This is a simply matplotlib function which plot the image with the projected coordinates. And then we can just see the same, more or less the same results of the GIS software without using GIS software. Then we can also move further and do some processing of this image, like the reprojection. Here we can describe why we are doing reprojection, which reference system we are moving on. So this is a geographic reference system because we want to in latitude and longitude to be in degrees. And then we can plot this. So we have the same, exactly same image, but now is in geographical coordinates and not anymore in projected coordinates. But then, thanks to Python and other Python libraries, we can move even further. And then we can plot like an interactive plot directly within the Jupyter notebook itself. So for example, this is based on GeoViews, that is a library for visualizing spatial data in Python. And then we can zoom in, zoom out, more or less the same thing that we have done in GIS, or we're doing GIS, but also we can implement it further with additional layers. So we can plot additional layers, we can plot additional color maps, we can plot really, or even different version of the same image. For example, we want to crop it further to change the color bar or do some additional processing. For example, if we are working on hyperspectral data, we can work and plot different hyperspectral slices or band combination, for example, three specific bands while like for some specific RGB composition and others in both in side-by-side views or overlaid, and so we can also having a processing and plotting while documenting what we are doing. And this is really useful for data reproducibility. And also because you don't have to take into account too much the how to present your data, because those can be used directly as a presentation, for example. Those can be converted into a PDF or a PPT and so on. So Jupyter notebooks, especially the processing on Jupyter notebooks, can be really, really powerful. And so this is the end of the ARISE processing. So just to recap, we saw from the beginning the how ARISE acquired the data, and I'll just show. So here how the data is on the, or the data footprint are on the planet and on the surface, sorry, and then which are the commands that we can use and comment and describe further with all the parameters that we want to use. And that's pretty much it. So since we are running out of time also, I think, and I want to briefly explain also the NASA AMES stereo pipeline. If you have any question, write in the chat, and also on Discord, we can follow up on Discord if you have any question. But consider also that these those notebooks that we are preparing are completely open source. You can customize it, you can reproduce, you can change anything. We have also some specific notebooks for AROC, NAC, WAC, for CRISM, for Chandrayaan M-Cube, and so on. So it can be customized for almost any imager or spectrometers that is on orbit or was on orbit and acquired the data set. So now moving just briefly to the stereo pipeline. Here, as also mentioned yesterday by Trent, stereo pipeline or ASP is really, really powerful, is way more complex. It's harder to implement it into Python, despite there are some attempts like the ASAP, that stands for AMES Stereo Automated Pipelines, that is a simplification of a wrapper around ISIS commands. You can run it instead of one by one in groups. So it's really helpful, but still is harder to combine all together into a notebook. But you can still prepare a Jupyter notebook which contains all the steps that you performed with additional documentation like images or parameters that you're using, the data references, document references, and so on. So in brief, as mentioned before, ASP is based on stereogrammetry and shifts from shading techniques that involves the usage of stereo pairs, which means that are like a virtual version of the image of the same area, or sorry, of an area acquired by the same instrument or different instruments with slightly different angle of the acquisition. And this will simulate our stereoscopic vision. And this, through the stereogrammetry algorithm and shapes from shading techniques, can help to reconstruct the depth. So you can reconstruct the digital elevation models or the digital terrain models in this case. And it's pretty heavy task. In comparison, the ASP pipelines, depending on the parameters, the size of the data, the algorithm that you're using, can also take up 2 days, 3 days to use on the same machine or the same powerful machine, even with 10 cores, 20 cores, 100 gigabytes of RAM, and so on. So it's really heavy and usually is not really intended to be executed in consumer grade laptops, or at least you can run it, but bear in mind that it can take a lot to do that. So usually it's preferred to be executed in servers or clusters and so on, because it really resource hunger. So the commands are pretty simple, are less than ISIS, are simply 5 or 6, depending on the steps that you want to do. And then there are, of course, additional, but there are also some parameters that you need to address, and you need to, or configuration files that you need to provide to select, for example, which algorithm to be used to do this match of the analogous points. The analogous points are the points in both of the image that corresponds to the same points in the reality. So for example, if we see a crater in the left and the right image, all the points that is on the craters on both of the images. And this is needed to reconstruct the proper position and then the depth or the elevation of the area. And then there are the stereo parameters, the stereo command, which properly compute this point cloud image or point cloud file. And then using the PC align, this point cloud align, you use this point cloud align command to align your regional or small scale point cloud to the global, for example, digital elevation model created by MOLA or LOLA in case of the moon. Then this is useful because you need to lock the position and correct the position, the local position, with a global one. So you can also compare with LOLA and do further processing. And then finally, you can use the point to them command that simply convert the point cloud to a digital elevation model image and the corresponding ortho image. And then this can be done with really easy, or at least the basic workflow is pretty easy and straightforward. You just need to provide the left and right image. Then you can execute the command, passing the map projected version of those left and right image. You can do the alignment, the PC align, passing the global image and using the above produced files. And then at the same end, the point to them using the previous generated files. And then at the end, you will have hopefully a DM and a ortho image without issues, correctly placed and ready to be used in your GIS software or additional Python workflow or machine learning and so on. But you still need to provide or at least the problem, is to find the proper parameters that are necessary to produce a valid result. But yeah, this is really complex talk, so I invite you to try it a bit or read better the documentation before proper starting to use the ASP command. So first get used to the data itself. So how would this produce, which is ISIS data format and all the steps, and then you can move to proper usage, because doing this in a trial and an error could be really time consuming and probably is not the best way. So before doing that, it's best to understand each step at the best and then move it further with the proper processing. So from my side, that's it. So again, if you have any question, because I know that this is cumbersome, it may be cumbersome, a lot of codes, a lot of stuff happening, but feel free to write on Discord. We are almost all of us, we know about ISIS processing, so you will see plenty of help that can be provided. So. Let me see the question. No question? Okay.
There is one in the chat, Giacomo. If you can access also single pixel spectra with the.
I think this one, oh yeah, sorry. When you have, I think this one for the last talk, but yes, I can answer. You can access single pixel spectra. There are several utilities, but imagine that I can not show you, but I can just describe it. Imagine this. Imagine this being an hyperspectral cube or a multispectral cube in which the z, so the coordinates pointing through the monitor, is the pixel values of each wavelength. Then using or Python or a GIS software or other GIS proprietary softwares like NV with ideal language, you can always access the single spectra of each single pixel or a group of pixels. And this is usually performed while doing some clustering, but I'm sure that all of those questions will be explained also by Mario D'Amore in the Friday talk, or probably hands-on workshop, which will use machine learning to process hyperspectral data. But in general, we have also some, you can find on GitHub, on our Aeroplanet GMAP GitHub, other pipelines that are, or Jupyter notebooks to access the single data cube pixel spectrum. And you can plot it in different ways. You can download it and process it further.